Okay, so we're over here. We're quite a bit ahead, actually. So I'll probably finish early today. In fact, that seems to be the pattern now for a while, unless something goes wrong, quote unquote, like happened before. But I'll probably lecture a little while, and then I'll let you ask questions. When the questions stop, we can just stop completely. I know somebody had a question from the previous section. I didn't get to it yesterday, so I'll see if I can get to it today. Okay? So we see how that goes. Friday's quiz. I'm probably going to give you quite a bit of time. You're going to be graphing a rational function. Okay, so they're difficult. They're longer. You have to factor, find asymptotes, right? Find out in behavior what happens when x goes to infinity and negative infinity, and what happens when you approach, the number 3 or whatever from the left and from the right. Okay, so I'll give you more than the usual amount of time. In fact, I may give you even half the class period, or maybe even more. So how about I'm aiming for at least half the class period, so 25 minutes, maybe even 30 minutes to do the quiz on Friday. But same thing, you don't have to turn it in until after the weekend. Class begins on Monday, so you can even work on it over the weekend. So I'll break you into your breakout groups again, and you can talk about it, but you don't have to finish it on Friday, unless you want to. A lot of you have been submitting the quiz right after class. That's okay, but you have the whole weekend to work on it. Okay? All right, so I'll do some more problems from 3.5. I have all of this time to do 3.6. So again, I may go ahead and get started with chapter 4, but I don't have to, but we'll see how it goes. I'll be satisfied if I can just finish 3.5 this week. Then I have Monday, Tuesday, Wednesday to do 3.6, questions and answers, and then the test on next Friday the 9th, okay? And reminder for the assignment, 3.5, throw out number 11. And the last problem we're doing is 21, so skip 23 and on. Okay. Or maybe another way of saying it is change it to 1 to 21 odd and skip 11. Okay, so I'll do some of this, and some of you start thinking about some problems you want me to do from back here. There's at least one I want to show you because somebody asked for it last time from 3.4. But think of other questions you might have after I'm done next 20 minutes or so, and if not, then we'll just stop. Probably the same thing tomorrow. All right. Okay, so back to 3.5. So we were determining the domain of these kind of functions that have square roots. So last time we only did products, something times something, and I'll do quotients, but they're very similar. Okay. Then again, we're skipping 11. Then after that, we're going to start with graphing functions that look like this. Okay. So let me go do some more domain problems with quotients underneath the square root. Okay. So let me move the book. All right. So how about number 7, please? Okay. F of x equals the square root of 1 minus x over x plus 3. Okay, so conceptually, again, the concept is whatever I have under a square root, that whole thing has to be greater than or equal to 0. So there it is, that whole thing greater than or equal to 0. Okay, I was mentioning at the end of yesterday, you set the top and the bottom equal to 0. That says set top and bottom equal to 0. So 1 minus x equals 0, x equals 1. X plus 3 equals 0, x equals negative 3. So on my number line, I laid down 1, and I also laid down negative 3. And now what about the open and closed circles? Okay, if I plug in negative 3 here and here, well, negative 3 here is automatically a mathematical no-no. You'd have negative 3 plus 3, which is 0. You're dividing by 0. You're never allowed to do that. So open circle. Now, why is there a closed circle on 1? If you put a 1 here and a 1 here, 1 minus 1 is 0. 0 divided by anything besides 0 is also 0. It would say 0 is greater than or equal to 0. That's true. So here's an instance where one side is open and the other side is closed. All right, then I test the 3 regions again, region 1, 2, and 3. So something to the left of negative 3, something in between, something to the right of 1. Okay, so what's to the left of negative 3? Negative 4. Something in the middle, 0. And something over here, 2 or 3. You can pick 2. I picked 3 this time. Okay, again, I only want the sign. So let's consider the signs here. So plug in -4. 1 minus a -4, that's like 1 plus 4, which is 5. Positive. -4 plus 3 is a negative. So that gives me a positive divided by negative. That gives me negative. Is a negative greater than or equal to 0? No, that's false. Don't shade in region 1. Stays unshaded. Region 2, 0. 1 minus 0, positive. 1 plus 3, positive. Positive divided by positive, positive. Is a positive greater than or equal to 0? Yes, that's true. Shade in region 2. Region 3, I put 3. Again, notice I said 3 twice. So again, to distinguish the region 3 from the number 3, you use Roman numerals here, right? So if I put 1, 2, 3, the regular 1, 2, 3, you might confuse. You see, oh, there's a 3 here and a 3 here. Do you mean 3 and 3 or region 3 or 33 or whatever, right? But when you write it with Roman numerals, then you know there's no confusion about mixing up. Even though they both mean 3, this is region 3 as opposed to the real number 3. Okay, plug in 3. 1 minus 3, negative. 3 plus 3, positive. So negative divided by positive is negative. Is a negative greater than or equal to 0? No, that's false. Do not shade in region 3. Okay, so we only have one shaded region, this one, not counting -3, but you are including 1. So the domain, D is for domain, parenthesis, meaning don't include the -3, -3, comma, 1, bracket. Bracket means count to 1. So I'm including 1. I'm not counting -3, but I am counting -2.999999, which is right up against it here. Okay. All right, so that's how you tackle this kind of problem. All right, so I'll do another one that has a quotient, which is number 9. F of x equals the square root of x plus 1 over x squared plus 2x minus 3. That one over there. So first you have to factor that, right? How do you get 3? 3 and 1. And you need a positive, so the positive should go with 3. So square root of x plus 1 over x plus 3, x minus 1. Okay? And again, superficially, square root of anything must be greater than or equal to 0. So I copy all the mess underneath the square root, make it greater than or equal to 0. Okay, boundary numbers. What makes the top 0? What makes the bottom 0? Okay. Set the top and the bottom, numerator and denominator, equal to 0. Okay, so what makes this 0? -1. What makes this one 0? -3. What makes this one 0? 1. Okay, so -3, -1, and 1. Okay, what about the open and closed circle stuff? Okay, -3, if I plug in -3 here, here, and here, -3 here, -3 plus 3 is 0. 0 times that is 0. I have a 0 in the denominator. That's not allowed, so it stays open. For the same reason, you cannot plug in 1. If I plug in 1 here, here, and here, 1 minus 1 is 0. 0 times that is surely 0. So again, you're dividing by 0. That's a mathematical no-no. You can't do that. So that's also open. But -1 is closed because if you put -1 here, and here, and here, -1 plus 1 is 0. So 0 divided by this is surely 0. So your statement would say 0 is greater than or equal to 0. That's true. So closed circle here, open here, open here. All right, looks like I have 4 regions. Regions 1, 2, 3, and 4. So pick something here, 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 and here. Fortunately, there is a nice integer in all of these. Okay, region 1, to the left of -3, -4. Between these two guys, -2. And then region 3, 0. Region 4, how about 2? Okay, fraction bar, fraction bar, fraction bar, fraction bar. I plug in. Again, I only need a sign. I don't need the exact value, just a sign. Okay, so I plug in -4. -4 plus 1, negative. -4 plus 3, negative. -4 minus 1, negative. 3 negatives. So when you multiply and divide negatives, if you have 3 of them, you're left with a negative. Is a negative greater than or equal to 0? No, that's false. Do not shade in region 1. All right, do the same thing for all these. -2. -2 plus 1, negative. -2 plus 3, positive. -2 minus 1, negative. So I have 2 negatives, leaving me with a positive. Is it positive greater than or equal to 0? Yes, that's true. Shade in region 2. In region 3, 0. 0 plus 1, positive. 0 plus 3, positive. 0 minus 1, negative. So if a positive over a positive times a negative, the whole thing will be negative. Is a negative greater than or equal to 0? No, that's false. Don't shade that in. Finally, region 4, plug in 2. Everything's going to be positive. 2 plus 1 is positive. 2 plus 3 is positive. 2 minus 1 is positive. So you're only multiplying and dividing positives. That's positive. Is a positive greater than or equal to 0? Yes, that's true. Shade that in. All right. So domain, you got to be careful. I'm not including -3, so parenthesis, -3, comma, -1. But -1 gets a bracket because I am including -1. And there's another piece here, so U for union, parenthesis, I'm not including 1, 1, comma, all the way to the right means infinity. Remember, infinity and negative infinity always use parentheses. Okay. Negative infinity would always be on the left side. Positive infinity would always be on the right side. Okay. All right, so that's it for that one. Okay, now we're going to start trying to graph stuff with rational exponents. Okay, that means you have fractions in the exponents. Okay, so how do I do that? Okay, so a quick review of rational exponents. Let me show you this right over here. So if you have a fraction in the exponent, a to the b over c, you can interpret it one of 2 ways. Okay. The top number is the power. The bottom number is the root. I've got that over here. Power over root. Okay. Think of the root of a tree or a root of a plant. It's down, right? It's further down. So the down number is the root, and above is the power. So you can write it either like this, okay, where c is the root and b is the power, or you can write it like this. Same thing. C is the root, b is the power. Now, in actuality, when you have to compute these things, this is obviously easier to write. I mean, you don't have to write all those parentheses. But in computation, this usually turns out to be easier. You would normally start off with the root, because usually when you take a root, you make the number smaller. We like smaller numbers. And then you raise it to a bigger number. If you do this first, that means you're raising to a higher exponent first. You might get a number that's so big you can't deal with it. And then you take the root. Okay, so this is easier to write. I mean, you can tell, right? This one's easier to write. You don't have to write all those parentheses. But when you're computing, actually figuring it out, this is generally a little bit easier. Okay, and I'll show you some examples of that. So let's look at 8 to the 2/3. 8 to the 2/3. Okay, this can mean either this or this. Okay, so the power is 2, the root is 3. Okay, so I do a cube root and then a square. Let's actually do this. It's actually easier here. So what is the cube root of 8? What number times itself 3 times? A number times the same number times the same number is 8. That would be 2. Right? 2 times 2 times 2 is 8. So this thing inside the parentheses is 2, and now you square it, and you get 4. Now, you could also write it like this. Okay? But this usually turns out to be harder because this means do the 8 squared first. That means you're getting a bigger number. So 8 squared is 64, and then what's the cube root of 64? Some of you know it's 4, but not as many people would know that. Okay, 4 times 4 times 4. 4 times 4 is 16. 16 times 4 turns out to be 64. So you do get the same answer, but you can see it's a lot tougher. Okay. Now, here's another example where you really don't want to do this. Okay, 81 to the 3/4. Okay, the power is 3, the root is 4. Okay, so I could write it like this. It's easier to write without the parentheses, but I don't think I want to do that. You could do that on a calculator, but you'd have to figure out 81 cubed, right? 81 times 81 times 81, I don't know, you can use your calculator, then do the 4th root. But it's actually easier to do this because I know the 4th root of 81. What number times itself 4 times gives you 81? That's 3. 3 times 3 times 3 times 3 gives you 81. So this is 3, and then 3 cubed is 27. So you can see that was a lot better. A lot faster than trying to do this. All right, so I'll do problem 3.5, page 176, number 13. Try to graph x to the 3/2 minus 2. All right, we know how to deal with a minus 2. Right, so I'll just deal with x to the 3/2. Minus 2 takes the graphs and moves it 2 units. Which way? 2 units down. All right, so the first thing I thought I'd do is try to graph x to the 3/2. So it's the square root of x cubed. Even though I write it like that, it's easier to think of this. All right, so I'm going to pick perfect squares. And notice I'm not allowed to plug in negatives. So I didn't bother plugging negatives. Okay, so I'll plug in 0 and 1 and 4. Can you see why I chose 4? Okay, I don't want to pick 2. That's not going to be a nice square root. I don't want 3. That's not a nice square root, but 4 is a little bit better. Okay, so plug in 0. Square root of 0 is 0. 0 cubed is 0. 0, 0. Plug in 1. Square root of 1 is 1. 1 cubed is 1. Plug in 4. Square root of 4 is 2. 2 cubed, 2 times 2 times 2 is 8. Okay, that's enough for a rough sketch. So I did 0, 0, 1, 1, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's up here. So the red is x to the 3/2. All right, and we know what happens when I put minus 2. Just drop the whole thing down 2, but draw the same graph. So instead of 0, 0, you now have 0, comma, negative 2 down here. And just draw basically the same shape. So imagine the green graph is just 2 units below the red. Or just take that red one, shove it down 2 units, and you have the green one. Okay, so that's that. It also asks for intercepts and asymptotes. Okay, this graph does not have any asymptotes. We don't get close to any one line. This thing shoots up toward infinity, and this stops here. So there's no asymptotes. Intercepts. Okay, well, we have this point, 0, comma, negative 2. Negative 2 there. And it looks like it does touch the x-axis somewhere. So where it's here. Well, I solve y equals 0. Okay, so plug in y equals 0. 0 equals x to the 3/2 minus 2. Add 2 to both sides. 2 equals x to the 3/2. And then to get rid of the 3/2, you raise both sides to the reciprocal of 3/2, which is 2/3. Okay, so again, you have 2 equals x to the 3/2. Add 2 to both sides, right? Then to get rid of that 3/2, you raise to the 2/3 like that. So x is equal to 2 to the 2/3 p power. Okay, that's the power, that's the root. Well, 2 squared is 4. So as an exact value, we'll just say the cube root of 4. So there's an intercept at cube root of 4, 0. So you can see it's not a very nice point. So it's over there somewhere. All right. All right, so I'm going to stop there. That's as much as I was going to do. And it's now question and answer time. So I'll pick up from here tomorrow. But now if you have questions, you can bring that with me. I'm going to do at least one problem that somebody asked for last time. Okay, so 41 and 43, they're kind of similar. Okay, so how about I do 43 for you? Okay, so x squared over x squared minus 5x plus 6. Okay,
We already did that one yesterday.
I did that one?
Yeah.
Okay, maybe I didn't do, did I do 41?
I don't think so.
Maybe not. Okay, maybe somebody asked for 41. All right, thanks for reminding me. So I'd be just retracing my steps here. Okay, 41 from 3.4. Somebody asked for, I think. 3.4, 41. And yeah, I'm done with lecture today. So think of any other questions you might have after I do 41. And if you don't have anything, we're done. Okay, so f of x equals x over x squared minus 3x plus 2. Okay. 3.4, 41. Now, Friday's quiz will be something like this. They're not fast. Okay, you can't do it quickly. I can't do it quickly. I can't just say, oh yeah, you do this and this. It doesn't work that way. All right, so let's factor the bottom. X, a minus and a plus means they're both minuses. Okay. And how do you get 2? Well, 1 times 2, right? Nothing else. And there's no cancellation. Right, so vertical asymptotes, VAX, V-A-X, so it's x equals something. X equals 1, x equals 2. Horizontal asymptotes. So for horizontal asymptote, just look at the first thing here and the first thing here. It's almost like you just cover this up. Okay, what's x over x squared? Well, that's like 1 over x. So when x gets super big, the ratio is 0. So hay, H-A-Y, y equals 0. Okay. On a deeper scale, this is first degree, this is second degree. So when I plug in a big number, the bottom is going to win, which means the ratio gets close to 0. If I plug in a billion here and here, these drop into insignificance. It's basically x over x squared. So it's a billion over a billion squared. I know a billion sounds like it's pretty big, but a billion squared is much, much bigger. In fact, it's a billion times bigger, right? So the difference between a billion and a billion squared is like saying, what's the difference between 1 and a billion, right? A billion is so much bigger than 1. By the same logic, a billion squared is, well, it's a billion times bigger than only a billion, so to speak. Okay, so y equals 0. And let's see, intercepts. What do you get when x is 0? 0. 0, comma 0. All right, so even now, we have some information. Okay, x equals 1, x equals 2. Asymptotes. And y equals 0 is the same as the x-axis. So we get really, really, really close to the x-axis. Okay, and let's see. If x is a super big positive, these are positive. So I already know it's going to go like this. Positive over positive. Okay. If I plug in a super big negative, it'd be negative over positive. If I plug a negative in, if you square it, it's positive. These are insignificant. So it's going to go like this. Okay. A super big positive will give me a positive, close to 0. Super big negative will go something like this. And let's see, it touches the origin, it says, so 0, 0. All right, then see what happens when we get close to 1 and 2 coming from the left and coming from the right. So x approaches 1 from the left, x approaches 1 from the right, x approaches 2 from the left, x approaches 2 from the right. So this would be like 0.99, 1.01. A little bit to the left of 2 is 1.99, 2.01. And I make my sign chart. Okay, like that. So I can't see them both at the same time, so let me recopy this, okay? So x over x minus 1, x minus 2. F of x equals x over x minus 1, x minus 2. Like that. All right, 0.99 positive. 0.99 minus 1 negative. 0.99 minus 2 negative. So I have 2 negatives, which makes a positive. So that tells me y goes to infinity. We already know we have an asymptote, so it's either going to shoot up or it's going to shoot down. In this case, it looks like it's going to shoot up. So right away, I know that this is going to happen. Okay. So x approaches 1 from the left. Come on this side, shoots up to infinity. All right, now how about over here? 1.01. 1.01 is positive. 1.01 minus 1. 1.01 minus 1. Positive. 1.01 minus 2. Negative. 1 negative means y approaches negative infinity. Okay. So when I get close to 1 coming from the right side, it drops down toward negative infinity. Like that. Okay, 1.99. 1.99 positive. 1.99 minus 1 positive. 1.99 minus 2 negative. Negative. Y approaches negative infinity. Okay, so this thing must go up somewhere and come back down. How high up does it go? I don't know. It does not touch the x-axis because there are no more intercepts. Okay. So it just goes up and comes down somewhere. When you get to calculus, you'll actually learn how to find out that highest point. But don't worry about it for now. And finally, x approaches 2 from the right side, so 2.01. 2.01 is positive. 2.01 minus 1, positive. 2.01 minus 2 is also positive. That's a 2 here. Sorry if it doesn't look like it. So positive divided by positive times positive, positive. So that means y approaches infinity. Okay. So as I approach 2 coming from the right side, coming on this side, it shoots up toward infinity. So I would just make it go like this, and that's about it. So that's the entire graph it looks like. Right, so I wanted to give you that. Okay, that's that. Let me check the chat. Okay, yeah, please send me an email about attendance, if you would, please. Okay, otherwise, I think I'm clear. So if nobody has anything, we can stop. But now, tomorrow being Thursday, right? So I will just continue doing more of the graphs, let you ask questions. And Friday, most likely, I'll give you a lot of time, the majority of class, to graph one of these. As you can see, you can't do them very quickly. So that's the best that we can do with that. Okay, and I'll check the chat one more time. Okay, I don't see anything else. So anybody want to ask me a question now? You can either unmute yourselves or put it in the chat, but if not, we're done otherwise. Okay, and I'll just do some more problems tomorrow. So if this week I stop only at 3.5, we're good. I have Monday, Tuesday, Wednesday of next week to do 3.6, review day Thursday, and then Friday, October the 9th will be our third exam. And that, by the way, would represent halfway through the course already. Okay, that's it. Anybody else, please? Wait just a few more seconds. Either unmute or you can put it in the chat. Okay, we're done, folks. Okay, so have a good day, and we'll see everybody tomorrow. All right? Okay, bye, everyone.